Yeah, it's really a pleasure to be with you. I'm Dali, and I'm talking about transferring waste material to wealth in producing sustainable cement. So if I want to go a bit on my bio, so yeah, as I said, the topic is transforming waste to wealth by producing sustainable cement. So if I want to say a brief bio of myself, when I graduated from master, I started to work on consultancy relevant to dam construction project. And from A to Z, selecting the material, selecting the site, doing mixed design for concrete and mostly gravity concrete and hydraulic structure. So some of the things I come across was the heat, a thermal crack due to heat hydration of the cement, which made me to write a proposal and get admitted to Sheffield University to do my PhD. And finally, because you know that the most important things in thermal cracking for concrete is hydration of the binder, and you can work on binder to fix the problem. So working on that brought me to the alkali activation of pozzolanic material, which was actually no clinker binder, and it was geopolymer. And after that, working on different projects at different university to replace the cement by different material like fly ashes, slag, so working on high volume fly ash concrete or using base glass in concrete. So this type of things, and as you see in the images, I did loads of characterization for these binders to find out that how they behave and how we can use them. Also assessing the concrete we made with that, doing some non-destructive tests and durability assessment of this concrete in addition to the mechanical assessment. So this was briefly my bio. And now I'm really happy to be with Material Evolution as technical lead. So leading some scientists to activate waste and use that in sustainable concrete, which I think is a brilliant idea to go ahead to have a sustainable cement. Yeah, as you know, cement mostly are energy intensive, so it I mean consume loads of energy and have high impact in our environment by emission of CO2 in our environment. So and on the other hand, the waste we produce every year, which is not low amount of waste we produce, quite high amount of waste we are producing. So if we can manage to use those waste instead of landfilling, using in cement, we can have sustainable cement, and definitely we can have quite good benefit in our environment by reducing our landfills, conserving our resources, natural resources, which now is used in cement industry, and reducing the CO2 emission of the cement. So yeah, possibly you are familiar with these numbers. I mean, cement is in charge of around 8% of CO2 emission of the world. And if we go for concrete, which is the most consumable material after water, the second consumable material after the water, then 80% of the CO2 emitted to environment by concrete is because of the cement. And also 20% of building CO2 emission, again, is embodied carbon in the which is used as cement in the construction material. If you go with traditional, I mean, production of cement, I have shown here. So we need some material like clay and limestone and sand as more silica source, and I mean iron ore, which can help us for reducing the melting point of during production. So these are the four main material usually used in traditional production of cement, and as possibly you know, they should be quarried and crushed and transported to the factory, then milled and clinkerized, and after clinkerizing, again, cooling and grinding and packing to the construction industry. And I have shown in the right image how much energy is consumed and how much CO2 is emitted due to different stage, which I got from McKinsey, if I want to be honest with the reference of the image also. So as you see, the main, energy consumption and the main CO2 emission is based on the middle part, which is calcining and burning fossil fuel. So that consume around 3 gigajoule per ton out of 4 gigajoule per ton, which we need for producing cement. And also CO2 emission mostly is due to the calcining reaction and also burning fossil fuel. So 50% due to the calcining reaction and 30% due to the burning fossil fuel. So what are the ways we can use in cement and how much we have and how we can use? So based on the World Bank report, we had around 2 billion ton waste in 2016, and it grows to 2.5 billion in 2030 and 3.5 billion in 2050. So we have quite a lot waste, and this is without considering municipal solid waste and the construction demolished waste. And for manufacturing cement, due to the chemistry of cement, we just need three main elements of silicon, aluminum, and calcium. So here I brought a different group of waste and pointed to some of the challenges they have. So first of all, the best one is a metallurgic byproduct like iron steel slag, ferrosilicon slag, copper, zinc, and aluminum slag. But the thing is, because these type of materials during the process get high temperature, and if it be cooled slowly in air, then it spend a long time in that high temperature, then it have time to make some order crystalline material, which is less reactive. And we need to think of the way how we can reactive this material. The second group are ashes from power plants. So we have coal, fly ash, biomass, bottom ash, lagoon ashes, and these materials are inherently fine. So it needs special attention to handling and storage of these materials. And also they, for gaining strength when they use as binder in concrete, if they be cured at ambient temperature and we don't apply a special curing to them, possibly gaining strength is delayed. And one more thing for lagoon ashes, because of being deposit for a while, so it's in contact with water, and mostly reactive material like calcium, silicon, and aluminum is leached out. So again, the reaction of the material is reducing and also include a lot of moisture and based on sedimentation. So it aggregate and it makes some coarse material, which again, we need to grind to make it finer due to the spec of cement and use it as cement. Another are dust of the different factory like cement clean dust, lime clean dust, and ferrosilicon. Microsilica, which is a byproduct of ferrosilicon factory, but these dust again should be densified to be due to handling and storage, not to cause problem for safety, for health, and also for using this material. Again, the variation of different batches can be high, and possibly contain some hazardous material that we should be careful about the safety of using this material. There are mine tailing. Mine tailing has a good story. So for if we go to history of these, mine tailing is usually for extraction of mineral. And because wet processing is more effective, so you have some muddy liquid, which you can't landfill that normally. So for landfilling these things, you need to construct dam, which is called tailing dam. And history shows that because people don't want to spend that much on that to control the safety, then we had around 30 cases of failure during 2008 and 2018. And one of the big failure in 2019 was a Brazilian tailing dam, which is related to Whale Company, I believe. So it's good to think how we can straightly use these materials to produce other of our requirements like cement. So it's good. And as I said, the natural raw material is muddy liquid, so it needs dewatering and drying and processing to be used. And possibly containing some heavy metal, again, should be done some chemical treatment to, extract those heavy material. Other groups are mud, like red mud, like paper slurry, soil slurry, and these all, for example, for red mud, because it's the byproduct of aluminum factory. Again, there are loads of aluminum in that, and it's good to be used for producing cement, but again, health and safety should be controlled for these mud, and definitely it needs dewatering and drying also. There are agricultural waste like wood ash, sugarcane ash, rice husk ash. These materials have high moisture, and usually because we need to burn them and use their ash, it comes to 25% of the material to be used. Again, demolished material, we do construction demolishing. We have ceramic bricks, concrete, glass, quarry dust. Quarry dust is a good material to be used. So these materials should be treated and sorted, and if it is contaminated, be sorted and separated. And the most is municipal solid waste, which we have around 11 billion per ton produced, and quite a massive amount, but it needs to be invested for an infrastructure to be treated and to be used. So I said challenges they have, but they have a good impact also, which I believe that possibly is good to be used for producing cement and make it sustainable, especially looking at future. We have no choice, just reusing the material we are producing as waste. So it has massive environmental impact. So it reduces the landfill, reduce the CO2 emission, and conserve the natural resources. I know that it's around 50 years that some countries like Switzerland, France, and Germany have a co-processed cement plant, which means that they separate the combustible and non-combustible material from municipal waste solid. And for the combustible, they use as fuel, and non-combustible is going to be used as raw material. And this, comparing to incineration of the municipal waste, the advantage is that you don't have ashes and you don't have secondary material to be landfilled. As I said, 11 billion ton, we have municipal solid waste that we should think of that. And also as alternative fuel, when we use this material, we can conserve the high carbon coal and don't burn that to emit more CO2 in the environment. Also, some of these waste material like slag, gypsum, the calcium-based one, can be replaced to limestone, and we can conserve natural limestone instead of consuming that in cement. Some of them like red mud, which is good, resources of aluminum, and waste glass with 60% silicone in it. These can be used instead of clay to conserve the clay material, the natural clay material, and don't excavate that to use for producing cement. In terms of economy, these waste material usually are free, and usually industry even pay to manufacturer to take them. So the cost of raw material is going to come down, which we know that clinker has 60% of price of cement production. So the cost of the material is coming down. And also the energy we need to treat this material, for example, for slag and fly ashes, just we need grinding. And grinding has less energy than calcining and clinkerizing the material. So again, the energy is coming down. In terms of technical benefit, most of this material has pozzolanic activities, so definitely increase the durability of concrete if treated correctly and used correctly in cement. And we can have some material which resisted to fire. So it was shown that when I was working in Ulster, making facade and exposing to the fire to see that how much they resist to the fire, comparing to the normal concrete, and it shows that when we have the activated material, we can have more temperature resistant material. So that is another case, another benefit we can have. Also, the dimensions, some of the material like fly ash gives us more room to play and make more dimension stable material. So we can control the shrinkage and these type of properties of concrete. And finally, it's good for having a new application. So some of them like paper slurry possibly can make a lightweight concrete. So we all are looking for lightweight concrete. Some of these material makes much more lighter concrete for us. So yes, and how the process modification, as I said, all of these need processing. First of all, needs to be screening and sorting and screening. So the different materials should be separated, and different size of the waste should be considered to be separated based on the application. And some of them, as I said, need crushing, need drying. For drying, usually three types of drying. Passing hot air or, contact the material to the hot metal screen. So different way of drying needs to be used for drying these waste. Also, compaction is needed. As I said, for example, for dusty material, it's better to be densified and then we consume those material in our production. Some of them has high magnetic makes less reactivity. We can't activate those material properly, so the magnet should be separated. And based on having heavy metal in it, some chemical treatment, oxidizing or using acid for, extracting the heavy metal is needed, pelletizing and blending some of them to have the raw material for our cement. So if specifically I want to go for cement, we should see that what are the waste available around and what are our local waste. So identifying the suitable waste that we have and has those three chemistry elements, then processing them based on the, cement spec, which I can refer to 196. So based on the fineness, based on the everything, and then developing the blending ratio and again modify the process. So possibly we need to blend some of them. When we blend some of them, again, they become coarser. We need to make grinding them, some modification again needed. And then do the process control. As I said, based on the spec, we need to always do the process control to see that we are in the limitation of our spec. And controlling the emission and the cost, then will give us how much benefit we can get out of that. So some of them possibly needs high processing costs and is not beneficial. So after we find out that what are the local ways and how we can manage to make our cement, then we can evaluate them and find out that are they in line with reducing the emission and the cost, or something should be changed. And after this, which is, I believe, in laboratory scale, we can move to the factory scale. So different elements of the factory operation should be studied to accommodate our raw materials. So all the characterization needed for a factory, like fluidability of the powder, like density, like heat, specific heat as a specification, the corrosion, hygroscopy of the powder. So anything, influence the operation of the our operation element should be studied, and operation element should be retrofitting based on that. And then when the process was adjusted with that, then emission and safety measurement and these things come to the board to be optimized and do the trial optimization of the blend, and so go ahead with that. If I want to say very summary, I say that we should have these three elements, which are the major elements of producing cement: silicon, calcium, and aluminum. And then we can go for different activation, which can be chemical, which can be mechanical, and which can be thermal. So I put in order based on the simplicity of using that. Chemical is aggressive material and can dissolve our waste, and then should have the property to make again after dissolving again be jellified. And for mechanical is some aggressive way that you can change the surface, you can make a hot spot the surface of the particle to react together. You can break down the crystal, and you can bring the melting point, reduce the melting point, and based on these treatment you can have your binder. And finally, thermal activation, that if we want to use, definitely we need renewable energy, and somehow we should move that be energy efficient, our material be energy efficient. So all of these, I know that there are very big challenges. I brought some challenges and according to that, some solutions. So the main challenges is the variation of the waste. So different waste has different character and different are very variable. Even the different batches of one type of waste has quite a lot of variation. And I think the solution is standardizing the material and give some certification, waste certification. So if we standardize the waste and say that based on the process we have done, this is certified and can be used as raw material for cement, then possibly this challenge can be solved. Another thing is high investment in the processing, in initial processing, and that one possibly needs governmental encouragement and policy. For example, putting carbon costs in our material to be more realistic when we compare our material with traditional cement. If the carbon cost is there, then is more, comparable those material, and people move towards using more sustainable cement and concrete. Also, having some certification like LEED certification, BREEAM certification based on, assessing the efficiency of the material and how is environment-friendly material. These can be helpful to, encourage to and reduce, somehow compensate the high investment of production. Initial high investment of production. And the other one is regularity barriers that I think it can be solved by contribution and collaboration of manufacturer and waste producer. So waste producer much more better information they have, and if this knowledge transfer between the manufacturer and the waste producer possibly is helpful to know that what type should be used, where should be used, how should be used, so what's the treatment. So these things can be more clear. And for future, prospect, I think that we should go toward developing carbon neutral, which I think everybody is interested in it, and then increase the data for using AI and machine learning. So I don't think we have enough data for prediction and optimization based on AI. We should produce that and then use AI to make it optimize and then expanding the use of circular economy based on that. So yeah, I can say the conclusion can be that using waste as raw material is a step to having sustainable cement, and a significant environment and economic effect can be, and technical benefit can be come out of that. And definitely collaboration and innovation is needed to move toward have sustainable cement product. In Mivo, we actually have this idea, and then we are, assessing different feedstock to see that different ways how can be converted to cement as cement product. And we follow up different mechanism of activation, which I mentioned. So, and yes, the factory Alan mentioned in Wrexham, which is really proud. We have the reactor, and based on that, so we try to activate base as a cement product. And yeah, we want to make it digital, so have more data access, and then use AI and ML for optimizing this. So far, our product is a zero clinker product. So yeah, we produced the first one, which is a zero clinker, and is class 52 binder, 1-part geopolymer. So and it saves 85% of the carbon emission. But we are moving forward to make it much more better with using different type of waste, with using different type of activation systems, so to have hopefully many of them. And thank you, everybody. I see very experienced people. I don't know actually the fields, but I hope that I didn't make you tired by my speech or explanation. Any questions?
I was just going to say, do we have any questions? Yes.
Thank you very much for that talk. That was very interesting. Really loved the chemistry. What I wanted to ask is, you mentioned earlier about using metallic slag as potentially one of the sources. In the metallic slag, is there anything particular in the case of the elements that you can see as being both a hindrance to the process, but also anything that could also be an advantage?
Yeah, I think the size of crystal you have and the fineness of the material you are using for cement. So somehow when you increase the fineness, you increase the solubility of material to be sold and to be aggressive to make it as a binder. But you should have same time some crystalline to reinforce and gelify those binders. So these should be balanced, but being crystalline is, I think, an advantage for slag. Yeah.
Dermot.
Have you done any accelerated aging tests on the concrete that is made from this new cement to check that the performance does not degrade over time and everything's get very old?
What should be, what should be the reason for degradation you mentioned? I'm accelerated is somehow good, but because we don't know that that is the quite simulation of the situation, I believe that if you, for example, apply temperature for accelerate that reaction, then temperature is itself is an element which makes aggression, which makes deterioration. So you are not sure that is because of the temperature that you apply to that, or because of the material. So I believe long term should be done definitely. I know that everybody is interested in accelerated because of the time, but if you want really be sure and confidence, we should do long term, and definitely that is in line with what we are doing, and we are going to do some long term to be sure that the product is okay. Yeah.
Alan, you had a question?
I've got loads of questions, but I'll restrict it to one. Having worked in areas where we've looked at uses for slags, byproducts, other things, one of the things we find with these sort of products as raw materials, and you showed an amazing array of things that could be, was for economic viability. If you're dealing with low value wastes and you're making something that's, without being disrespectful to cement, it's not making diamonds or platinum. It's got a relatively low value. We've often found that we say, if you've got to sell slag as a byproduct, if it has to travel more than, let's say, 50 miles, you burn up all your potential value in transport costs. So how local?
That is why I mentioned in the process that it's be local availability. I'm quite agree with that. So starting with the company also, as somebody who's responsible for feedstock, I was looking for whatever we have locally, and I really appreciate the material be local available. And I can say that the more local available, the better. I don't say that how much, but I say the more local available will be better.
People who are online, does anybody online have a question? If so, can you unmute yourself and ask it, please? No? Okay, we'll carry on. And there's a question at the back there.
Yeah, I just want to say brilliant presentation. I've got two questions.
Can you speak up, please?
Okay, I've got two questions. One is, you mentioned different types of activation: chemical, thermal, and mechanical. Is it possible for us to have a mix?
Yeah, combination. Yeah, I agree.
To have better
Yeah, yeah, combination. Yeah.
The second question is, what we've seen with SES, especially when we talk about environmental assessment, is that the lack of long-term data means that because we don't understand how this would behave in the next 5 years, the next 10 years, the next 20 years, means that just this inertia to adopt it. So have you had thought about some kind of correlation between the durability of the product and also the environmental aspect? I don't know if you thought my question right.
Do you mean that the effect is in durability and the effect is in environment? I can say so far I am not confident to answer this question, to be honest with you. And yes, definitely, as the other question was, long-term evaluation is really important for this material, I believe. But some of them, I think, because, for example, we use geopolymer, I think, from 1960, something like that. So some of the material has shown that they are durable after that time. But as I said, more, confidence is needed to be sure that, and it's obvious that the lower, chemical you use, possibly you can be more confident about your material. And I have seen in what I have done in lab that possibly mechanical activation is much more how to say comparing to chemical. So if you use mechanical activation and low chemical, then possibly you help to the durability also. And some of these materials, like microsilica, which has been used even in traditional concrete for increasing the durability, can help us for making it more durable.
I mean, just to obviously with using waste feedstock, you could have some elements that are very dangerous to the environment. They get into the water system, they get into the sewage. So it's really important that we have the long-term proof.
Yeah,
to
I agree.
data. And concrete is being built to last 50 to 100 years.
Yeah, I agree.
Time you could have some deterioration. So
Yeah.
So nice question. Thank you.
You're welcome.
Have we any more questions? Alan,
Well, if there's somebody else take that.
Michael first, and
Yeah,
then we'll go to Alan.
So, okay, so you haven't got long-term data, how long this new process is going to last, and we've heard horror stories about, what was it, the aerated concrete that was supposed to be all the rage in whatever it was.
Right, in the 60s.
Exactly, in the 60s. So are there applications where you could sort of trial this, really want to build the A19 bridge out to substandard concrete, that'd be silly, wouldn't it? But I was thinking like, I don't know, in curves my garden or something, that's where you can trial this. I don't really care.
Yeah.
So, I'm going to want to rip it out in 5 years. Anyway.
Okay. Good.
Alan?
I was very pleased to see your mentioning the amongst the bewildering array of potential starting materials, trying to look at things like machine learning and AI to try and help characterize.
Yeah.
With such an array of different raw materials, how long does it take to actually work out what a new mixture or a change mixture or a new raw material is capable of and how it should be used?
I think first of all, the more data we have, we can train the AI much more better, because AI is something you are training and you get feedback from that. So if you don't have enough data to train the AI, then that's not going to work perfectly to get feedback. That's why I say that for my opinion, possibly I don't know, but for my opinion, I think there is a way still, and we need to work with different material and produce data, then train our AI to get feedback from that.
Yes.
What's your main material streams that you see as being big success stories in the next 5 years? What kind of input stream are we actually targeting?
Between these materials.
Because this could work with almost anything to anything.
Yeah.
What do you see?
It depends, because if you think of the most waste in the world possibly is working to do some on demolition stuff. It is 6 billion ton per year. And for municipal solid, it's difficult. That's why I don't suggest that, because it's quite difficult to be treated. But the nicer material, I can say, are different slags, based on what has been done so far and what we can do.
Mining like historical deposits.
Yeah, that also, I'm not sure about the, I believe that possibly if we want to use mining at this stage, we still need the tailing dams. If it's possible, I'm not sure, I should learn from somebody which is working with this material for extracting. If it's possible to use that straightforward, then it's really worth it to have a look and see that how we can convert that. Because as I said, people don't spend to make that structure for, reserving those tailings, and that may fail, and then, so, yeah.
You'll be focusing on the fines and the activated the binders, basically.
Can you speak up a bit, please? So that
So your presentation has been focusing on the fine end, the fines end of the market side, and on the binder side. Are you finding these activated binders are more comfortable with certain types of aggregate for the bulk of the concrete production, or Is there anything you can say about that? Do you need to do anything different with the growth, with the aggregate when you're making it?
In terms of packing, yes, I can say. In terms of packing density and controlling that, possibly, yes. Yes.
Okay. Does anybody online wish to ask a question? No, evidently not. Well, I think we'd like to thank Dali in the usual way for her excellent presentation. It's obviously inspired a lot of interest and quite a lot of questions. So, a small gift for you to say thank you.